Okay, in Unit 8, we're going to be working with what are called radicals. And radicals is basically just this symbol right here. Most of the radicals you've probably worked with are square roots, but we use the general name radicals instead of always square roots because sometimes we might have a cube root, we might have a fourth root, we might have a fifth root. So radical is just the general term. And then square root, cube root, fourth root, fifth root are a little bit more specific. So in this first section, in 8.1, we're going to be working with simplifying expressions with square roots. So first of all, just kind of a quick review of what a square root is. So if you think about your numbers, like we have 1 squared, remember that means 1 times 1, that's 1. 2 squared, 2 times 2, that's 4. 3 squared, 3 times 3, that's 9. 4 squared, 4 times 4, that's 16, and so on. So the square root is basically the inverse of that. It's saying, so if I have the square root of 1, it's saying what number times itself gives you 1? Well, 1. The square root of 4 says what number times itself gives you 4? Well, 2. The square root of 9 says what number times itself gives you 9? 3. So it's the inverse of squaring something. You'll notice right here that if we take the square root of negative 81, we're going to get undefined. And that's because taking the square root of a negative number is going to give us a non-real answer. And we'll work a little bit more closely. Whoops, see if I can spell answer. Answer. We'll work a little bit more closely with this, with the negative square roots a little bit later. But as we work with square roots, so if I give you this, the square root of 100 is 10. The square root of 81 is 9. The square root of 49 is 7. We get nice whole answers here because each of the numbers underneath our square root is what we call a perfect square. But what we're going to see in this unit is that not all numbers have a nice even square root. Not all numbers are perfect squares. So if we take the square root of 8 and we type that in our calculator, we're going to get this really, really long decimal. Your calculator probably won't give you that many decimals because it's not big enough. And that's a rounded approximation. That is not an exact answer. So usually when we're working with square roots, we want to be as accurate as possible. So we're not going to use the calculator to help us find the decimal approximation. We're going to learn how to rewrite our radicals in simplest radical form. So I'm actually going to show you 2 ways to do this. And for each of these 4 examples, I'm going to show you both ways. You do not have to do it both ways for every single one. Pick which one makes the most sense for you and just stick with that. So if the first one I do makes the most sense, then just fast forward me talking through the other one. So one thing we're going to use is what's called the product rule of square roots. And that's this right here. If I have the square root of something times something, a times b, I can kind of split those up into 2 radicals. I can write that as the square root of a times the square root of b. Those are equivalent. Okay, so the reason that this is helpful is when we have something like this, the square root of 75. If we type that in our calculator, we're not going to get a nice even number. It's going to be, let's see, 8 point something, something, something. So if that's the case, that means that this number right here is a non-perfect square. So if we want to simplify this, if we don't want the decimal approximation, the first way I'm going to show you how to do this is we are going to use a perfect square that we know, and it might be helpful to come over here and list some of our perfect squares. So let's see, 1 squared is 1, 2 squared is 4, 3 squared is 9. If we keep going, 16, 25, 36, 49, 64, 81, 100, 121, 144, blah, blah, blah. So we're going to try to break this number up into a product of a perfect square and another number. So if we kind of think about our perfect squares up here, which of those perfect squares is a factor or will go into 75? Well, 25 will. So I'm going to rewrite this as the square root of 25 times 3. 25 times 3 gives me 75. So I didn't change the value. I just wrote it as 2 factors. Well, my rule up here says that if I have this, I can really write it as the square root of 25 times the square root of 3. And we talked about above the square root of 25 because that's a perfect square. The square root of 25 is 5. And then we keep the square root of 3 there. So if we simplify this, we get 5 square roots of 3. So that's one way to do this. Think of a perfect square that will go into this number right here. That is a factor of that number. Rewrite it using that perfect square and continue from there. Sometimes, though, that's hard for people to do. Sometimes it's hard to look at 72 and say, okay, what is the biggest perfect square that will go into that? So another option to do this is using what is called a factor tree. So we're going to use a factor tree for 75 to write the prime factorization. And when I say write the prime factorization, prime numbers are numbers like this: 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. They're numbers that their only factors are 1 and that number. So we can use a factor tree to break this up. I could think of 2 factors of 75. We have 3 and 25. Once I get to a prime number, I'm going to circle it. The factors of 25 are 5 and 5. They're both prime, so I circle them. So I'm going to rewrite the square root of 75 as 3 times 5 times 5. And then I'm looking for groups of 2. I'm looking for pairs. So we've got a pair of 5s. Whatever pair that we have, we're going to take that number to the outside. So 5 is now on the outside. If we take that pair to the outside, I'm left with the 3 on the inside. And notice we get the same thing, and I want to explain why this is. If you think about this pair of 5s right here, well, pair of 5s, 5 times 5 is really 25. If I take the square root of 25, I get 5. So we're essentially doing the same thing right here. And right here, we're looking for perfect squares or pairs of factors. We're just going about it 2 different ways. This one is probably quicker if you know your factors pretty well. This one is probably more reliable if you're less confident in your factors. Okay, so on all of these, I'm going to do it both ways. Pick your favorite method. Okay, so on example 379, we have 5 times the square root of 63. If there's a coefficient in front of it, remember that means they're being multiplied together. So I'm going to start thinking of some factors of 63. I'm going to think of which ones are perfect squares. Well, I know that 9 is a factor of 63. So I'm going to rewrite this as 9 times 7. Okay, my product rule of square roots right here says that we can rewrite it like this. The square root of 9 times the square root of 7. Well, we know that the square root of 9 is 3. It's a perfect square. That's why we chose that number. So we really have 5 times 3 times the square root of 7. If we simplify those numbers out in front being multiplied, 5 times 3 is 15, square root of 7. All right, let's do the problem one more time, but using the factor tree method. So I'm going to take 63 and I'm going to do a factor tree to find all my prime factors. You can start with whatever number you want to. There's multiple ways to do your factor tree. I'm going to do 3 and 21. 3 is prime. So I'm going to do 3 and 7, and both of those are prime. So if I rewrite this, I'm going to keep the 5 on the outside so we don't forget about it. 3 times 3 times 7. Well, we've got a pair of 3s. So I'm going to take a 3 to the outside. There's already a 5 right here. So when I take that 3 out, we multiply them. 5 times 3 is 15. The only thing left over inside is 7. So either method we use, we get to the same answer. Okay, similar on example 380. We're going to do our 2 ways. Let's look at our perfect squares up here. We're trying to find the biggest one that we can. That's just going to make the process a little bit more streamlined if we find the biggest one. That will go into 72. Well, we know that 36 will go into 72, and it goes in 2 times, so we're going to write this as 36 times 2. My product rule from above says we can write this as the square root of 36 times the square root of 2. Well, 36 is a perfect square. The square root of 36 is 6. Then we still have that square root of 2. If we're doing this using our factor tree, 2 factors of 72, you can start with any 2 you want to. I'm going to do 2 and 36. 36, I'm going to do 2 and 18. 2 and 9. 3 and 3. So if we write this out, I've got the square root of 2 times 2 times 2 times 3 times 3. Well, in this one we actually see 2 pairs here. We see a pair of 2's and we see a pair of 3's. So I'm going to take a 2 to the outside, I'm going to take a 3 to the outside, and the only thing we didn't circle, the only thing that's left over is that 2. If we simplify our coefficients on the outside, we get 6 square root of 2. Either method, same answer. All right, and then our last example that they gave us right here, we have we've got some variables here. And I'm actually going to do it the prime factorization way first. So I'm going to start on this side, and then I'll go do it the other way. So I have negative 5 square root of 18x to the 4th, y to the 6th, z to the 10th. So if we find the prime factorization of 18, I have 2 and 9, 3 and 3, and I'm going to rewrite this as negative 5 square root, and I'm going to make this really long. I'm going to write really small here, of 2 times 3 times 3. And the reason I did this is I want us to remember that x to the 4th is really x times x times x times x. Y to the 6th is really y times y times y times y times y times y. And then this is why maybe this method is not always the simplest. It can be a little bit obnoxious at times. Z to the 10th is really z 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so just like all the other ones, we're looking for pairs. For my numbers, I only have a pair of 3's. There's already a negative 5 on the outside. Negative 5 times 3 is negative 15. And then the only number I have left over inside is 2. All right, if we think about our x's, I've got a pair of x's, pair of x's. So it's like I'm taking out an x and an x. Well, x times x is x squared. For my y's, I've got 1, 2, 3 pairs of y's, so y to the 3rd. In my z's, I've got 1, 2, 3, 4, 5 pairs of z's, so z to the 5th. And notice I didn't have any letters left over inside of there. They all were in my circled pairs that I brought to the outside, so I only have that number of 2 left. Okay, if we go back and do it the other way, I'm looking at 18 and thinking of, what am I trying to say? Thinking of the biggest perfect square that will go into that. And that's 9. I'm going to write this as 9 times 2. Then I'm going to keep that x to the 4th, y to the 6th, z to the 10th. All right, we know that the square root of 9 is 3. Negative 5 times 3 is negative 15. And then we can kind of do the same thought process here without writing them out. We're thinking, okay, if I have x to the 4th, how many groups of 2 or perfect squares can I make with that? Well, x squared, and there's none left over. Y to the 6th, that gives me y cubed, no leftovers. And z to the 10th, z to the 5th, no leftovers. So I have this 2 left over on the inside. Okay, I'm actually going to add just a really quick extra example right here of what might happen if we do have some leftover variables. So if I have x cubed y to the fourth. I'm going to just kind of think through this one without writing it out like we did right here. So if we're simplifying this and I'm thinking of x cubed, how many pairs can I make with that? Well, I can make one pair, but I don't use all of them. I have one left over. But my y's, if I have y to the fourth, I can make two pairs with that, and I don't have any y's left over. So if we do have any kind of leftovers in our numbers when we're making pairs, they just stay on the inside just like our numbers do. And that is how we simplify non-perfect square roots. You can do either method. You do not have to do both methods every time. Please do not do both methods. Just pick what works for you on those.